right, so we're going to get started with cisp310. And let's first check how many people turned in.
Don't forget to record it.
Homework assignment.
Are you recording?
The recorder is on. I just turned it on, but I'll double check. Yep, it is on, and if I look at the command prompt, it is ticking, so that's
All
it.
right.
All right, so we'll check the homework assignment first and see how many people turned in.
If it's less than a certain number, would it get pushed back one day or something?
Well, I was planning to do something like that. 24 out of 43, not bad. I will keep it. No, I'm going to push it back to Thursday. So the due date is going to be Thursday. It doesn't mean that if you got it done already, you're going to lose anything. Okay, so if you got it done already, good job. If you have kind of poured in a lot of time, it doesn't seem to be working. It's not a waste of time either, because every time the program doesn't work and you figure out why it is not working, that's the best way to study for this class. It really is. Okay. So what we do want to talk about today, so first thing first, let's change the due date, and so it will be on the 5th of May. And I know some people are pretty close. I know some people are getting really close. It's just not exactly, there yet. And I can explain certain things that might be helpful. So we'll go ahead and do that today. All right, so I have just changed the due dates to Thursday. You have 2 more days to do it. So what we want to do today is to go through a few common problems that people do have. How many people are struggling with make or the make file at this point?
Yes.
Okay. All right. So what are you guys getting? What is bothering you about the make file?
Well, originally it was because you didn't put the video up until this week, so that's why I couldn't figure it out. But
Oh, okay.
I think I will be able to get it resolved.
Okay.
Yeah.
Yep.
I had a question for, we're doing our include file or whatever.
Okay.
Is that just like we have to have it made?
Yeah,
outside
the
of
include file is a little bit of a tricky case. So I want to show you guys why it is tricky to begin with, and then I'll give you the quote unquote, it's more of a hack, but it is a solution to fix that problem.
You're recording? I was doing like touch and then complex dot
Yeah.
IC.
Yeah, but I want to show you why that is the case, because I think you probably already know or at least get a pretty good sense of the reason why it's not working. Okay, so let me just kind of show you the dependency graph first. Okay, so everything starts with complex.h. Okay, because this is the file that defines the structure of complex. It is used by all the C programs. Okay, and that's why it is particularly useful. So I'm going to use an arrow to indicate whatever's on the right hand side depends on complex.h. So we got main.c, we got complex.c, and then we also got complex test.c, all depending on complex.h. Now, but you have to write your own C program to generate the include file, right? So that program is actually has one of these dependencies. I'm not sure how you define your own, your own executable. So I'm just going to use define struct as the name of that particular program, which only have one single purpose. Okay, the only purpose of this program is to generate the include file that you will also need to put into your assembly language file. Is that okay?
Mm-hmm.
Okay. So this is the original, state of the entire thing. When you start to write subroutines in assembly, then you will start to have complex add.uppercase s as a file. Okay. So you have complex add.uppercase s. Now this is where things get a little bit complicated, because there's no way I can put a dependency from complex.h directly into complex add.s, even though that kind of expresses what needs to be done, because I want your complex add to be insensitive to how the complex number is defined. I should be able to rearrange the elements or the members of the structure add additional ones and without impacting the correctness of your code. So we want something to be related between, we want a relationship between complex.h and complex_add.s, but not directly. So what is happening here is this define struct.c in return creates define struct itself as an executable. That in return creates complex, complex.inc. That in return is pound included by complex_add.s. So this is the picture, and this applies obviously to the other subroutines as well. The problem is when we do a make clean, it removes all the files that are generated, including the include file. But in order to regenerate the .d file, which are the dependency file, the compiler wants to recompile complex_add.s, which will fail because the include file is missing at that point. Is that okay? So there are two ways to fix this problem. So let me go to a make file. Let me see if I have that already saved on this computer. Yep. So when we look at the make file here, this one is kind of really plain to start with. So I'm going to make changes to this one to reflect what you guys have to do. So I have define struct executable being just define struct, and then we have define struct src, which is the source file, which is define struct.c. Obviously, I don't have that file just yet. And then we have this include file, which is complex.inc. So this is the step that you eventually have to do this part. Now you also have to add the targets. So we're going to put $define struct exe depends on define struct source, but change all the .c to .o. And that should be it. Okay, that should generate the define struct exe file, the executable. But we also need one more rule. We also need to say that the include file inc depends on define struct exe, and the actual way of doing it is run define struct exe and redirect the output to the inc file. Okay, so I think most of you have gotten this part already, or something equivalent to that. Yep.
Okay, so the define struct exe all caps, that could be anything you wanted it to
Oh
be.
yeah, I'm just choosing a long name to do it.
What is the advantage of doing that instead of actually using the file names?
It just makes it more flexible. I mean, you don't have to do it this way. I mean, you can just use the actual executable name here. You just have to do it consistently. That's all. Okay. Question? Yep.
Can you go back to the where you
Document viewer.
Yeah, document viewer. It's about define struct.c. What is that?
That's the one that generates the include file. That's the one that will take a look at the structure and look at the number of bytes between a particular member of the structure versus the beginning of the structure.
That's what you were doing the other day.
That's what that file is.
So that has to be part of the
Make file.
part of the assignment.
Yes, it is part of your homework assignment.
Okay.
Yep. Mm-hmm.
So, as far as changing the definition of the structure, does that just mean changing which variables where in the, or would you add variables to that? 'Cause
I can add members. The only thing I cannot change is the type of I and R. So I cannot make I a long and expect your program to work because that changes the type.
All right, so you can add members anywhere, but you won't actually try and use those members, just I and R?
Correct.
All right, good.
Okay, so based on what we have here, okay, this is the changes that we have made. So clean has to be changed as well, okay, because clean has more items to clean now. So you have to clean dollar define struct src dot c equals dot o, because that's an object file. It can be deleted if you want to start everything clean. Define struct exe itself can be clean because it's just an executable. It can easily be recompiled and relinked. And there's also the include file. Now this is the part that is kind of tricky, because when you remove the include file itself, then it will have a problem to regenerate everything. I'm going to go through the whole thing just to show you guys what the problem is, and then I'll talk about how to solve this particular problem. Yep.
So can you just not remove the
But you may not have that ink file to begin with, so you will still end up with that issue.
Forgot to read.
So to make it all go away, to make clean really, just reset everything to a known state to begin with, we'll use the touch method. Yep.
So all of our other functions like print and complex test would also have to go through define struct.
Yes.
Similar.
Well, no, they all depend on the inc file, complex.inc, which is the output of define struct. So that means as you define more and more subroutines, each subroutine has its own source file, but they all depend on the include file, because the include file is telling you where to find each member that you need to know in a complex structure.
But a complex test has its own header file, so how would that, would you have to create a different define?
It doesn't, that one is not important, because when you look into the content of that file, I'm going to save this first, and then we take a look at the complex test.h. See, this one does not have its own structure definition, so this is not needed in assembly at all. This is only needed when you use C and C++, because we need the prototype so that we know how to use ABC as a subroutine.
Okay.
Is that okay? All right. Okay. So for the purpose of this particular program, I'm going to write a fake define struct. .c doesn't do a single thing. It compiles, but it doesn't do anything except it still has include complex.h and main, but then it doesn't do a single thing. Okay. Obviously, this is just a fake executable. It compiles, it has the right dependency, but it doesn't do a single thing. And let's just say that I'm starting to write one of these subroutines. Let's say I'm starting to write complex print. Okay, so it has its own source file now. So we say .global complex print return, which means it compiles. It's going to provide a subroutine. You can call the subroutine, but it doesn't do a single thing. Okay. Okay. So let's say this is the first subroutine that I'm implementing. I forgot one thing. I forgot to do the pound include complex.inc. Now this one cannot pound include complex.h because complex.h is written in C. The assembler doesn't understand it. So this one can only be using the include file that has label equals to number, label equals to number, because that's the only thing that the assembler understands. Okay. So at this point I have everything in place except in the make file. I also need to add in the assembly source file. Now we have complex print.s as one of those. And now I can go back to complex.c and comment out the original print subroutine. Yep, go ahead.
Jack, I know you said in Linux there's no such thing as types, but why do you put inc? What does that mean?
Include.
So it's just an include file?
It's just an include, but I don't want to call it .h. It's not a header file.
Okay.
Yep. Okay. So now we have everything in place. We say make, and it's going to have a problem because complex.inc is not there. So it will stop compiling. It will start compiling, quote unquote, compiling complex print.s. And this is not compiling, it's just trying to figure out what is the dependency. So we have a chicken and egg problem because in order to find out what is the dependency, we run into a problem. Okay? So the solution to this problem is in the make file. There are two ways to do it. You can do it by hand, or you can put it into the make file. After the rm or the remove instruction, basically it's just delete. You can just say recreate.inc by touching it. In other words, touch is updating the timestamp of a file that does exist, but if the file does not exist, it will create the file at a time and make it an empty file. Okay? So this will solve the problem. So when you say make this time, make clean first, sorry. So you have to make clean, turn the whole thing back to the original state, and then make, it's still having a problem.
I don't think you made a rule for make clean for the clean part for
The clean should be there.
it's all the way at the bottom.
We have a clean target, so there's a clean target.
Well, what about those includes all the way at the bottom? Remember you said you have to add something there in the make file?
Okay, let me just do a make clean first. So the make clean says blah 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 blah. Blah, blah, blah. It did not go through that, so I do have to make this one externally. Now it does it. Okay. So the touch cannot be, you can build it into the clean, but the first time you do it, you still have to touch it first. Okay, because it's a chicken and egg problem. So you gotta have, you gotta make that one chicken magically first. All right, so is that okay or not? Okay. All right, so getting on to the actual content of this program, okay? So we'll go through each one, in the subroutines, and we'll deal with the easiest one first, okay, which is print. Because print does not return a structure. All it does is having a structure, which is called A as a parameter, that is passed by value, which means the entire complex structure is on the stack itself. So what you need to do in this case is really just to define the literal string itself in assembly language, and access the individual members, R and I, to print it out. So I don't think this is going to be a big problem, because I think we have gone through examples in class that are pretty close to this one. Okay. So this is not going to be a big, huge issue. Yep.
This is just complex underscore I.
Complex.
Like when you're transferring.
It depends on how you call the labels, because the labels is based on how you define those in define struct.c. Okay, so this one is not too big of a deal. Now this one is a bigger deal, okay, because you're still you have two parameters for one thing, okay, but two parameters versus one should not be a big problem, because we already know the second parameter is pushed on the stack first, so it has a higher address. So the first parameter, in this case A, has a lower address than B, but each one is a complex structure, so don't allocate just 4 bytes for each parameter. You have to know how many bytes to allocate for each structure on the stack. Okay? So this one is a little bit more complicated, but not too bad. It also has a multiply instruction, which means you have to use the mul instruction, M-U-L-L, which is multiply long. This is add, which is easier than multiply. So for the most part, this file doesn't have anything that is really, really bad. But when you look at complex test.c, then we have something that is kind of nasty. Because when you look at line 6 here, we have kind of a complicated thing going on, because we have a subroutine call, and I'm using the result of a subroutine as a parameter to another subroutine. So the question now is, okay, so how do we work this out, okay? So how many people are kind of stuck with this one, and how many people, okay, so good. All right. Getting stuck with this one is not a bad thing. It means you guys worked through the other ones already. So that's good. All right, so what we want to do is we want to look at the stack from the perspective of complex, let me see which one, from the perspective of complex add. Okay, now I understand normally we want to work from the inside out, but this time we want to work from the outside in because we want to set everything up so that eventually when we call complex add, we don't have to move a whole bunch of stuff around unnecessarily. Okay? All right. So from the complex add perspective, what should the stack look like when I call that subroutine? This is the outer part of the subroutine. Okay. So I'm going to draw that picture here. From the perspective of complex add, we want the stack to look like this. We want parameter, the second parameter to be already set up here, and that turns out to be my parameter C. Okay. We want the first parameter set up here, which is right below that. And that's the result of complex mode. So I'm just going to say C underscore mode here, because I don't have enough space to put everything. And I think A, B are the parameters to the multiply subroutine. Is that okay so far? And by the time we call complex add, we also have some other stuff that we have to push on the stack, including a return value pointer, and also the call itself will put the return address over here. That's not going to be a big problem, okay? So we are not too concerned about these two little items. We can always deal with those later. So that means, you can set up C over here to begin with, okay? And how do we set up C over here? Okay, let's take a look at how this entire frame looks like by the time we get to this call. The entire frame should look like this. ABC as a subroutine takes on three parameters. Okay, let's go back to the definition of ABC. It takes on three parameters. It has parameter A, which is a complex. It has parameter B, which is a complex. It has parameter C, which is also a complex. So when you look at the stack, we have parameter C, and then we have parameter B, we have parameter A, and then we have this return value pointer, pointing back to some location that is supposed to store the result. We don't know exactly where it is. We just know that whenever we store the result in the return statement, that's where we want to store it. That's all we need to know about this pointer. We also have the return address here, which is pushed by the call instruction. And then because of the push old EBP or push EBP, we have the old EBP already saved here. EBP should be pointing to the base of old EBP because that's how we set up the pointers. So EBP pointing here, and then we have our local variable. Do we have? Yep. Okay, we have a local variable X, which is down here. So this is probably how you set up the stack, and I'm pretty sure that most of you know how the frame is supposed to look like at this point. Okay? So let's just say that at this point we are ready to call to deal with that statement, to deal with this statement here on line 6. So the first thing you want to do is to reserve the space and copy C over here to set up for the call. Okay. Do we know how to do this? You adjust the stack pointer, and then you do mem copy. Okay. So the next thing you want to do, which is really the most crucial part, the next part is to reserve this space here, which is for the first parameter to complex add. I'll just put it here. This is the first parameter of complex add. Okay? Because C is the second one, this is the first one. Okay. So you want to reserve that space. And then after that, okay, this is something that you can do by because the camera is moved when I move the paper. So when I rotate it, yeah, that sort of works. Okay. Maybe move.
It'll look fine on the video.
Yeah, it will look fine in the video. It's just that the projection screen itself is a little bit out of alignment. The other way, the other way. There we go. Okay, so now that we have that space already saved, the next thing we need to do is to call complex mode. How do we call complex mode? The usual stuff, right? So if I line this up correctly, that will work out even better. There we go. Okay, so when we call complex mode, we'll basically use this space here and say, okay, this is where B goes, because B is the second parameter to complex mode. And then we push A over here, which is the first parameter to complex mode. Is that okay? So this is the key, okay? The key is, where do we want the return value pointer to point to when we call complex mode? Which is this pointer here. Now, it's smaller because it's only 4 bytes. This is just an address. It only has 4 bytes. So this is our return value pointer or address, however you want to call that is fine. We want that to point back to this space over here. That's the trick. Okay, the rest you use usual stuff. Okay, so then you call the complex mode subroutine, which will automatically push the return address. Okay, so when complex mode is done, it would have done 2 things. It would have put the product of A and B into this space over here, which is the first parameter to complex add. So that part is done already. It would also undo both of these bytes. So when complex mode returns, these 2 bytes or these 2 locations, these 8 bytes will be deallocated. So you are left to only have to undo, the 2 complex numbers. So you have to reclaim that space. Then you're back to this picture over here, right? And when you're back to that picture, you have to set up the return value pointer itself, do the call, and then let everything else be done by complex add. Is that okay? Okay, so if you're really just stuck with this one function, I think that key has to do with, okay, once again, I need to reline up everything. There we go. So the key is to set up this return value pointer to point to the space that you have already reserved for the first parameter to complex add. So this way you don't have to copy things around like crazy. I mean, you could do that too. I mean, you could reserve that space early on and then just copy a lot of stuff around. But this way you don't have to copy too much stuff around. I have to be careful where my fingers go, because you just saw that, right? So are there any questions about this? I mean, are you guys getting how to set this up? Okay, cool. Anything else? Anything else about this homework assignment that you're getting stuck with?
Just craziness, as I showed you earlier.
Okay, that I have to take a look at the lab, because it's not something that I think is easily explained, so I have to actually see it. Not to believe it, I believe you. It's just that if I see it and I can interact with GDB, I can find out more about why it's happening. All right. Anything else? Any other questions about this homework assignment? Mm-hmm.
So how is I and R like stacked? Like when it's on the stack, it's like R and I?
Okay, that's a good question. So the question is, how is I and R related in the structure, right? That's the entire purpose of define struct.c, because I really don't know how the compiler wants to arrange those 2. So let's just go to the code that we have here, and we'll actually finish we'll just actually finish this whole thing. So we'll say pound include stdr.h, but I really don't want to finish the whole thing, so I'm gonna give you something that is okay. I is this many bytes from the beginning. And we cast everything into void pointers. That's how it works. So we say complex C, and we take the address of C dot I here, and then subtract C itself, or the address of C from that. Okay. And here's the R. Okay, so I'm assuming you guys have something like this in your define struct or whatever is equivalent to define struct to find out the displacement of each member from the beginning of the entire structure. And I really don't know, exactly how that's going to work out, so we'll take a look. Define struct. Or better yet, I can say make complex.inc. And it complains because request for member I in, okay.
Did you pound include complex?
Did I what?
Did you pound include complex?
I thought I did. Yep, I did. And it's complaining C is not defined. Complex H. It has complex in it. Okay, let me just read the error message one more time. In function main, unknown type name complex. Oh, I know why. This is one of the things about C versus C++. See, in C++, you never have to say class, complex, and then the name of the variable, but in C, you do. That's why. There we go. Okay, it's still failing because there are 2 warning messages, expects argument of int, but those are just warnings. I will fix those.
If you use this char pointers.
Yeah, but it's complaining define struct is not found. Oh, because it's compiling it to define struct.o, and it's linking it to define struct. Oh, I know why. That's a Unix thing. Because it has to do with when something is in the same folder, you have to say a / to run it because it's not in the path. Okay, and we'll go ahead and fix the warning because I should practice what I preach. Which is just telling the compiler, yes, I know what I'm doing. Don't nag me.
It's all good.
Well, this reminds me of something that I just dug up today. I'll show you later. Finish this first. Okay, it's still failing. Okay, no such instruction. Oh, that's because it wants to compile with it. Okay, fine. So it works. So complex.inc is actually created. It says I is 0 bytes from the beginning of the structure, R is 4 bytes from the beginning of the structure. Now, given this, okay, this is how I'm going to test the program. So when I test the program, I will give you a different complex.h header file, and I can do something like this. Okay, I can reverse the ordering of the 2 members. Okay, let's see whether this will make any difference. Okay, so make complex.inc. Oops. Okay, that's not. It's supposed to work. Now it works. That's interesting. It didn't link the relationship between. Oh, that's no straight relationship. That's why. Okay, so when I do the regular make, it does remake it. So when you look at the include file, this time it says oh, it's the same. Okay, I'm missing something. I know what I'm missing. I forgot to specify the rules.
Did you put the include at the bottom?
Hmm?
Did you put the include at the bottom?
The include
For the
Make file.
for define struct exe.
Oh, you mean this part
Yeah.
here? Oh, yeah.
That's what I was saying earlier.
Okay, thank you. So we want to include define struct source dot c, oops, lowercase c equals dot d. There we go. No wonder it couldn't figure out that dependency because it's missing that part. Okay, now we got it. So you can see that I and R are now reversed because I just changed the ordering. But this is not the limit of what I can do. I can also do something like this. Okay, go back to complex.h. I can just, pad it with something. So I want to define a buffer of some kind that I'm not going to use, and let's say 56 characters. And this time complex.inc will actually take that into consideration. So the R is now 56 bytes from the beginning of the structure, and then I is 60 bytes from the beginning of the structure. So I can do all of these things, to kind of test whether your program will take that into consideration. Is that okay? All right. Any other questions related to this homework assignment? No questions? You're all becoming experts of the makefile.
Slowly.
No one else teaches it.
A lot better than.
No one else teaches it.
No, but everybody expects you to know it.
If I recall correctly, we used one in Fox's class.
We used one in Fox. That doesn't mean he taught
It
it.
looked differently, and we were told
Not to touch
not to mess with it too much.
Okay. Well, I can tell you that I do write software, kind of not commercially, but as a consulting job. So I do make some money out of it. In other words, I get a 1099 miscellaneous at the end of the year because of that, and I have to pay taxes for that. But it's not really a lot of money. It doesn't even cover the equipment that I have to use to make it happen. But anyway, in that project, I do have like a lot of lines of code, a fairly complex project with many source files. And I just do everything just like what I do in class. I have a makefile. I maintain the source file of the makefile, and I don't use a GUI. I don't use any IDE to do all that type of development. I just don't find any use of a GUI unless I'm dealing with something that's a lot more complex. Has anyone tried to write software for mobile platforms, like for the iOS or for Android and stuff like that? Now with that, yes, I do like to have Android Studio because it's not just an editor, it actually makes it easier to look up information. That's the added value. But when it's mostly my own code and I don't need to look up a lot of stuff, this is all I need. Okay? Now, I will bet you when you look into the makefile of other classes or when other people talk about makefiles, they do not make things like this, which is very general. Because when you look at this makefile, if you have any additional source file that you want to add, you just expand this line. And as soon as you add more items here, you say make clean and then make, it will automatically take all of that into consideration, including the dependency on header files and whatnot. You can have one header file that depends on another header file. It will take that into consideration too. So this is basically the template of all the makefiles that I personally use. Now sometimes I have to tweak it to do one thing that is extra that this file doesn't do, but most of the time it suffices. I mean, this is doing what I normally do. Okay? And what are the chances that I would personally have projects where I have to mix assembly language source file with C source files? Pretty good probability, or do you think not a chance? I mean, that's just what crazy people do.
Probability, oh my God.
It's possible.
Well, I will tell you that's what crazy people do, but I'm one of those.
Okay.
And okay, this is kind of
Optimized.
a little bit related to this class. It's also a little bit off, of the usual topic of this class. I'm just going to bring you to my website, which is really archaic. It's really old, and hopefully I started the virtual machine and it's running. Well, maybe not.
I think I timed out the last time I tried to connect to it.
Okay.
Archaic by the graphics are 16-bit.
No, it's just I haven't updated it for a long time. Okay, maybe it's not working. Darn. Okay, maybe I got everything over to the other website. I'll check it. Google. There we go. I still have it over here. See, I clone my website all over the place, so this way if one server goes down, I still have somewhere else to go. So I go to teachers, and this is actually this is when I taught EEC 194. Maybe not here. Go back. Develops. There we go. So what I do is I wrote my own real-time kernel, and if you want to read about it, you can just click this link here. It's a real-time kernel, which means it is kind of a operating system, but it doesn't have a file system. It only deals with processes, threads, and the synchronization of threads and stuff like that. So I wouldn't call it a full operating system. It's really just a kernel. But when you write code to use this multi-threading kernel, I have the API. The API, which programming language do you think the API is intended for? Just by reading the description of the API itself. It's for C, exactly. So even though the real-time kernel itself is 100% written in assembly, the API is actually written for C. Does that remind you of something about this class, especially at this point with your homework assignment? Yep, exactly. That's exactly what it is. So I have sample code over here. Okay, this is one sample program where you include rtk.h, which is a C header file with all the prototypes and a structure definition of a thread. This is all written in C, but the assembly code actually uses the same type of mechanism that we talked about in this class. So the assembly code also understands what is a struct. What is a thread struct? It's just that it's defined differently. And the rest of the program is written entirely in C and C++. Okay, in C in this case. So this is just initializing the thread and making it the first thread, the highest priority thread of the real-time kernel, and doesn't do a single thing about it. Okay, this is just sample code. It doesn't do anything useful. But that's basically linking back to what I just wanted to point out, which is the make file that I talk about in this class is a direct product of what I actually personally use in some of my projects. By the way, how big do you think this real-time kernel is? In terms of footprint, like how many number of bytes does it use and stuff like that? Does anyone want to guess? Okay, so
200 megs.
okay, well we'll take a look at concepts that is actually going to be related to this class eventually. It has got the concept of a thread, okay, which means you can have multiple threads that are executing quote unquote in parallel within the same program. That's what multi-threading is. They can share global variables, but each one has their own call stack, so they can be calling subroutines without interfering with each other. So the real-time kernel allows that to happen. It has time slicing, which means if one thread is not giving up control, you have time slicing, which is basically saying, oh, thread A, you have been executing for 5 milliseconds already. It's time for you to give up control and let thread B begin. Okay, so it's got multi-threading like that, which is called round robin. It has got priority queues, which is basically based on priority. You can have a queue that has a higher priority and a queue that has a lower priority. Until the high priority queues have nothing to do, the low priority queues do not start execution. So that's prioritization, because with a real-time kernel, the whole point is things that need a quick reaction time can react quickly. Things that can wait a little bit, okay, we'll wait a little bit. It's no big deal. What else does it have? Just looking at the interface here, you can schedule. Okay, look at this part here. It has a way to schedule, which means you can schedule a thread to basically sleep for a certain amount of time, and just say, wake me up in 200 ticks. Okay, whatever amount of time associated with each tick depends on hardware factors, but you can just basically say, okay, I don't need to do anything until 2 seconds later. Okay, and I don't want to consume time in between, so it has scheduling based on that. Some of these concepts you probably have no exposure to at this point, which are semaphores. And semaphores are basically a mechanism so you can synchronize multiple threads. You can basically say, okay, I'm waiting here for something. So that particular thread will stop and have a flag and say, I'm waiting for something. Another thread can be doing something else that will eventually be done so that the waiting thread can start execution again. So semaphores is a mechanism so you can synchronize the execution between these threads. Okay, one can wait, the other one executes, and then the other one can signal the first one and say, okay, I think I got what you need, so you can now continue. And so it has got all of these features. It's completely 100% written in assembly. The source code is, I cannot remember how big, but the after everything is compiled or assembled, is 8 kilobytes. As in 8,000 bytes. That's the size of the code itself. In terms of space, I think it uses up maybe 500 bytes or something like that of memory. So it's a pretty small footprint. You know, it works. It's not really for publication or for other people to use. It's really just my little pet project for the summer. And at the time, the only tool I had to debug this, and you guys would say GDB because tech likes GDB. No, not on this platform. This is on the chip itself. The chip is not big enough to have any type of operating system. And at the time, I was too cheap to buy actual hardware debugging tools. So I was debugging the whole thing using 2 LEDs. Yep. Did it light up? Yes, it lit up. Okay, we got to that point.
Yeah.
Yep. So it's kind of a little fun project. But that really helps us to kind of segue into something that we do have to talk about in this class.
I have a question.
Yes?
Are we ever going to review the last test?
The last test.
My God.
Oh, we did. I just have to post the video. I did it in the lab. Okay. I did not forget. Unlike some ex-presidents.
Tisk.
Oh, no, he did not recall. Okay, I stand corrected. And it's not something trivial either. All right, so we'll talk about I/O, input, output, and interrupts. Okay. Now, this is an interesting topic. It's really hard to describe and actually do anything with some of these topics, but the other topics are really, really useful. Okay, it explains a lot of stuff that we kind of like, how did that happen? How does an application program talk to the operating system and then have the operating system to do something for it? Okay, so we'll start with interrupts and system services, which is this link here. I may not have fixed the link. Yes, I did not. Okay. So I can fix the link, or I can just go back to the other tab that I have already opened, because it really is the same place. Oh, I closed that one too, did I? Okay. All right, so this is a trick that I want to show you guys where to find all my stuff. You just go to boodle.losbrios.edu/TAUYEUNG, and then you go to teachers, and then you go to, oh, maybe not that. Okay. I think it's teachers and the modules. That's not. Yep. So module will give you all the notes that I have written, but not recently. These are all kind of individual notes and stuff like that. But if you go back one level to ARC, you can find quote unquote a textbook for this class. So if you go to ARC and then go to cisp310, this is really old stuff. You can find some other exams, but you can see also the dates. So they're not really particularly useful for our class. But the textbook is here as well. So if you look into the textbook, that's the stuff. Okay, this is the actual quote unquote textbook, and I just have individual links to these sections from Moodle. So all of the stuff is actually here. And we are looking for operating systems, input output, requesting operating system services. before we talk about that, we have to talk about interrupts. So there we go, interrupts first. Okay, so interrupts is a hardware concept. In other words, in order to explain interrupts, technically speaking, we have to go all the way back and use Logic Sim to show you the picture of that whole thing, okay? But let's explain what is the idea of an interrupt. Now, let's think about what things would look like without interrupts, okay? So let's just say that you are writing an operating system like DOS, okay? Where there's an end user that can be typing something on the keyboard, and your job is to run, you're writing the command line interface, the CLI. So you're interpreting what the end user is typing on the keyboard and say, okay, when the user presses the enter key, then you want to parse whatever is typed on the line and figure out what to run based on what is typed. Is that okay? So that's the assumption that that's what you're doing. So what would you do? Well, here's the keyboard, okay? The keyboard is attached to the USB controller these days, and then the USB controller has a whole bunch of what we call I/O registers, not to be confused with the registers inside the processor. They're called I/O registers, which basically are accessible by your program. And looking at the individual bits of these I/O registers, you can tell whether there has been an event on the keyboard. If there's an event on the keyboard, then you can extract the event, figure out which key is pressed or depressed, and then based on that, we can figure out what the user is typing. You can say, oh, okay, the end user has just typed or just pressed the backspace key, so I have to erase the previous character, and so on and so forth. Okay, but the bottom line is, how do you know the end user has done anything on the keyboard? Okay, you are writing the command line interface program, and your job is to interpret what the user has typed on the keyboard so that you can deal with backspace, you can deal with pressing the enter key and stuff like that. Yes?
Expecting something?
Expecting something. So your program is expecting something. But how does your program know whether a key is pressed or not? Because your whole program is waiting for that event to happen. But how do you know that it has just happened? Sorry? You can poll. Okay, very good. Okay, so the first method is to poll, P-O-L-L, which means your code is going to look like, well, maybe I should use not this, but this. I can just type a lot faster this way. Okay, so your code may look like this: while no key event, do nothing. Okay? Now, obviously, this is pseudo C code, but you can kind of get the idea that you're stuck in a tight loop and you're just repetitively checking whether there's a keyboard event or not. Okay? So when there's a keyboard event, then not key event is going to be false, and you get out of the loop. Then you go ask the keyboard controller or the USB controller and say, hey, keyboard, give me your last keystroke. Okay? Tell me what has just happened. But there's a problem with this approach. What is the problem with this particular approach?
Stalls the thread.
It stalls
The thread.
the thread, okay? In other words, if you're dealing with a multi-threading program, this thread is getting in a tight loop, and nothing else can do anything within this thread. But if you have multi-threading kernels like the one that I just mentioned, well, you can still do time slicing, and other threads can still do what they're supposed to do. But this will still chew up processing time, okay? Because the processor is actively executing instructions just to check whether there's a key event or not. Is that okay? It's not efficient, for one thing. Excuse me. And it certainly is not energy efficient. Might need to drink a little bit of water first. So this method is not efficient. Think about the same thing on your cell phone. Okay, so I'm going to get back as soon as I get a little bit of water. Okay, so think about this as your cell phone. Okay, Your cell phone stays in your pocket for the most part, not doing anything. At least you're not supposed to do much with it during class, right? But your cell phone, doesn't know that. It doesn't know that you're in class and you're not going to be interacting with it. Using the polling method, it's going to be checking with the touch screen all the time, right? It's going to ask the touch screen controller and say, is there a touch event? Where is it? Is there a touch event? Where is it? It will keep asking that question, which means it's going to be using the processor to keep executing those instructions. What's going to happen at the end of the class when you say, okay, I better text somebody or to arrange someone to call and pick me up? Your battery is dead because it has wasted all that energy by asking the touchscreen over and over again, is there a touch event? Okay, so it's not energy efficient, let alone being time efficient and other things that we like. Okay, what is a better way to do this? Let's go back to the keyboard thing. Yep.
Like if you press a key, then the key will go.
Yep, exactly. So when you press a key on the keyboard, we want the keyboard controller, which is not consuming nearly as much energy as the main Intel processor, to basically create an event. And the event is sent back to the main processor in the form of an interrupt. And the interrupt is going to interrupt, guess what? The program execution at the time and say, excuse me, processor, we got something to handle now. That's an interrupt. So this is hardware related because it is completely transparent to software. Yep.
On the phone, is the digitizer pretty much a way of interrupt?
Yep.
Is that what it's?
Yep.
for?
So on the cell phone, what's happening is you do have multiple controllers. They're not full processors per se, but they do have processing ability, but they're not quote unquote programmable. So your touch screen has one of those. And you don't need a high-end processor. You don't need like a gigahertz clock, combined with 64-bit, ALU, just to figure out, whether you have touched the screen or not, right? So that particular processor also doesn't have to run very quickly either. How fast can you draw something? How fast can you do a hand gesture on your screen? Does it require like 3 gigahertz type of processing? No. Well, I mean, if you need that type of processing because you can draw things that quick, you probably need a lot more scratch-resistant screen because you can be doing things so fast you'll be like starting to melt things. So you can only do things so fast, which means the processor, the controller that is actually responsible to detect any type of touch event on screen only needs to run at the most maybe kilohertz, hundreds of kilohertz. Okay, so it's not going to consume a lot of processing power. But when there is something to do, okay, for instance, I think mine is somehow set up to the tilt sensor. Okay, so when there is something to process, then it will send a request. It will send an interrupt to the processor. Now the interrupt to a processor is basically just a signal to inform the processor that, hey, there's an input-output event that I need your attention for. That's all it is. Okay. Imagine my office, okay, or the office of any professor. So here is, okay, so here's the office of any professor, some professor. Okay, so here's the door, and here's the desk of the professor, and here's the professor falling asleep, okay? Okay, so on the outside of the door, okay, so here's the door, you have a switch. The switch is the interrupt mechanism. The switch is actually turning on a light bulb here, okay, so we'll just say this is a light bulb or lamp on the desk of the professor. So when you walk by and you say, okay, I have a question to ask Professor so-and-so, then what you're doing is you flip on that switch. So when the switch is on, it is lighting up the lamp inside the office. The professor may be doing something that is non-interruptible. Okay, what we call atomic. An atomic operation means it is something that cannot be interrupted. But at the end of that simple task that is non-interruptible, the professor will take a look at the lamp and go like, oh, okay, somebody is outside, and want to ask me questions. Okay, so at that time, what the professor would do is to put down what he or she was doing right before, put a little bookmark in the book just to remember where he or she left off in the book, or have some other way use a post-it to say, okay, this is where I was doing, this is what I was doing before I answered the question, just so that the professor can resume that operation later on. And then the professor will call the student in. When the student walks in, the first thing the professor will do is to turn off that light. Okay, is to basically, well, there's several ways to do it. When the light is turned off is actually kind of debatable because there are different ways to deal with it. So basically the student walks in, interact with the professor. When the student walks out, then the light is going to be turned off. At that time, the professor will look at the bookmark or the post-it, continue to do what he or she was doing before until the lamp is turned on by another student again. Is that okay so far? Is that analogy working? That light switch is the interrupt mechanism. When the light is on, it simply means there's a request to interrupt. Doesn't mean the processor is getting interrupted. It simply means there's a request to interrupt. When the professor is done with whatever is not interruptible, then the professor will go, okay, let me go answer the question and handle the interrupt. Is that okay so far? Okay, so now imagine this. Imagine the professor is doing something according to a huge, big, manual. Something that's really, really clerical. Like screening interviewees for a faculty position. Okay, it's really boring, long process and stuff like that. Okay, so the professor has been doing this, not sleeping, and you walk by, you turn on the light. Okay, so what the professor is going to do is to first, finish whatever is not interruptible with the screening of the interviewees. Okay, put in the last entry into the worksheet or whatever. Okay. And then the professor will put a bookmark onto the last page of the instruction manual so that the professor can remember, okay, before I got interrupted by a student, I was doing this. Okay, and then close the operation manual, ask the student in, and see what he or she can do for the student. During all that time of answering the question, the professor is following another set of instructions, digging up other books from the bookshelf to answer the question. Okay? Using up some scratch paper, post-its, and whatnot. When it's all done, all of that stuff is put away, and then the professor can go back to the interviewee screening and continue from where it was left off because he left the bookmark where he left off. Is that okay? Okay. It's exactly the same thing with the processor. It's just that when we're executing instructions, okay, let me go pull up a particular sample program, just so that we have some reference to all of this stuff here. Okay. I'm just looking for one that has a folder that has something to demonstrate. We can just always just write one to begin with. So I'll just write a really trivial test program in assembly. And we already know all this stuff here. I'll just do this really kind of useless, completely useless program. To make it extra useless, I'll do this. Okay, I'm hoping that most people can look at this program and say, yep, that is pretty useless. Okay, so let's say this is the program that I'm running. And as I'm running this program, there are lots and lots of stuff going on, like networking is going on in the background. Okay, this computer is constantly receiving packets and have to process stuff. The timer is going off, okay, so that I can keep track of time and stuff like that. So what is happening is between the execution of these instructions is quote-unquote interruptible. Within an instruction, it is not interruptible, but between instructions, it is interruptible. So that means, and that's regardless of the complexity of the instruction. In other words, I can have a fairly complex instruction like mul with a memory operand, okay, something like that. Okay, so it will take multiple steps because I have to get one of the operands from memory, do the multiplication, store the product into EAX and EDX and stuff like that. That is all uninterruptible. Okay, from the time that I start the execution of the multiply instruction to the end where I store the product into EDX and EAX is uninterruptible. But right after that, right before I execute the next NOAA instruction, the processor will look at the lamp and say, okay, does anyone need my attention? Oh yes, okay, the lamp is on. So at that time, the execution is not going to the next instruction, and instead, the processor will first remember, okay, since somebody else needs my attention to do something else, I'm going to remember where I left off here. And where do you think the processor is going to store the address of the next instruction to execute? Where do we usually store the return address? It's on the stack, okay? So, and then right after that, the processor will use a particular lookup mechanism to find out, oh, I can see that it is the USB controller that needs my attention. Let me go to the quote-unquote subroutine that deals with the USB controller. It's called a vector table, which is basically just a table. And let me switch back to this part here. So the vector table is really nothing more than a table of addresses. So you have a table of addresses, and which entry you're talking about depends on what device and what is the event that you're handling. So I'm just using this as an example. USB controller may take up one entry. Your SATA controller may take up another entry. Your network interface card may take up another entry. Now this is a gross simplification because typically one single device may have multiple entries here. Like for the NIC, you might have one entry for receiving something, you have another entry for transmitting something or done transmitting something. But what the entry is it points to a subroutine. Okay? It points to a subroutine, and the subroutine contains the logic to deal with whatever can request attention from the processor. In the case of the USB controller, it might be something just got plugged into the USB bus. It can be a USB device on the USB bus transmitting something. It can be the host finishing transmitting something to one of the devices on the USB bus, but it has to be something that the USB device itself or the USB hub itself says, okay, I'm done doing this, I don't know what to do next. I better ask the operating system. Okay? So this logic here is going to be, this is called the ISR, or interrupt service routine, which is basically a subroutine of sorts. Okay, it's not exactly a software subroutine, but it has all the properties of a subroutine, including the last part of a subroutine. What is the last instruction of a subroutine? A return instruction. So in this case, it is a return instruction with an I after that. It's a return from interrupt instruction, which is a little bit special. In addition to looking up on the stack and saying, okay, I'm done processing what needs to be processed here. In this case, I'm done, working with the USB controller. Let's go back to where I left off. That's what the return instruction is. But return instruction, return instruction is a little bit more than what we usually expect. But let me explain why and how it is different. In your code, do you think in our assembly language class here, even if I give you the location and the instruction, do you think I can just convince the SATA controller to wipe the hard drive clean? And why not?
Kernel tells it no.
Okay, first of all, the rationale, the why first, okay? Why would you not let a normal user process have access to the I/O registers that can directly tell the hardware what to do? Like in this case, you tell the SATA controller and say, okay, just write all zeros to all sectors of all tracks. Why would that not be a good thing?
Horribly insecure.
It is very insecure. Now, if you're just wiping a hard drive, it's not too bad. But if you're reading the hard drive, you can steal information from the hard drive. That's actually worse than wiping a hard drive clean, is to steal information from the hard drive. So that means, we don't want we don't want just any user process to have access to these I/O registers. Okay, does that make sense? What about the operating system? Okay, so I'm in an application program. Let me just pick one. I go to media and I say I want to save a file, and I specify the path and stuff like that. Why do you think in that case I have access to the hard drive and actually save some content on the hard drive? Who's doing it? If the individual user process cannot work with the hard drive directly, then who is saving all that content onto the hard drive? Because something has to boil down to the actual interaction with the SATA controller to really save something onto the hard drive. So who's doing it? The operating system, okay? So the operating system is the actual one interacting with the hardware and say, okay, let's go and send this packet to that particular IP address. Let's write this information to this sector. And oh, by the way, the keyboard just interrupted. Okay, we'll grab that key code and do something about it. So that's what's happening with the operating system. So that means the operating system needs access to all of these locations. The interrupt surface routine, the ISR, is a part of the operating system, which means it also needs access to all of these important I/O registers. Is that making any sense? That is the big difference between a normal subroutine that we have talked about so far in this class compared to a ISR, which is an interrupt surface routine. So in the process, okay, so let me just go back to this prop here. In the process of going from the mode instruction into the ISR, in this transition here, there are several things that are happening that normally is not happening when we just call a subroutine. First of all, the privilege level of the processor is going up. In other words, when we are surfacing an interrupt, the processor will automatically say, oh, let's go, increase the privilege level so that in the ISR we have access to all the necessary input-output registers. Is that okay? So the first thing we do here is to elevate. Okay, there we go. Elevate privilege level to access I/O registers and other resources. And then the ISR would actually do its own thing. Okay, so process the interrupt, which usually means remove the cause of the interrupt. And when this is all done, when the ISR or the interrupt surface routine is all done, what do you think it has to do to make, quote unquote, the return? Now, if it just do a normal return, like an RET instruction, that means the elevated level to access I/O registers will remain to be there when you resume control in your code. Would that be a good thing? So during the execution of your program, okay, normally you don't have access to those I/O registers, but because an interrupt happened and the return instruction did not do much about the elevated level of access, when it returns, you now have access to all the I/O registers. Would that be a good thing? Probably not, right? So the hardware, when you execute an RETI instruction, return from interrupt instruction, it would do one extra thing. It would adjust privilege level back to where it was before the actual return instruction. So this way, the interrupt is by itself, self-contained. It will increase or elevate the privilege level, do whatever it needs to do with that privilege level of access, and then when it's ready to return, it will also adjust the privilege level back to where it should be, and then it will return back to your process, so that your process can continue execution. Are we doing okay so far with this stuff here? It's all talk, I know, but that's basically the concept of interrupts and how ISRs are structured. Okay. So now the next question is, okay, so now we know what happens when you press a key on the keyboard, or when you are ready to when you're ready to send something over the network and stuff like that. The next question is, how does this have anything to do with the operating system? In other words, you have something to do, you want the operating system to do something for you. How do you make that request? Let's look at it from the perspective of C first, okay? And then we'll talk about how it is done in assembly, probably on Thursday and not today. So we'll take a look at some really low-level subroutines that you can actually call in C. This is a subroutine that you can call in C. It's called read. It doesn't do a whole lot. All it does is you have to supply what we call a file descriptor, which is basically just an integer. Internal to the operating system, every file that you open in a process has a number associated with it. Think of it as the ID number of a file, okay? So you use an integer to identify a file that you have already opened. The second argument is just a buffer, which is, okay, you want me to read something? Where do you want me to read it into? So buff is where it's going, this is the pointer to the location where the content is going to be copied into. And you can also specify the number of bytes that you want to read from that particular file. In other words, this is all really just saying, hey, operating system, this is the file that I want to read from. This is where I want the content to read into. This is the number of bytes that I would like to read, but sometimes it may not read that number of bytes. And by the time when you're all done, tell me how many bytes you actually read. That's the return value. So you might request to read 200 bytes, but if only 10 bytes are ready to be read, then the operating system will return and say, okay, sorry, I only read 10 bytes, but I did read all of those, or overwrite the first 10 bytes of buff to reflect the 10 bytes that I just read from the file. Is that okay so far? Okay, you can do this in C. Okay, this is actually C callable. So now the question is, if you can do this in C, how do we do this in assembly? Okay, first thing that should come to our mind at this point would be something along this line. Well, we just push all the parameters. Okay, we push, oh, I want to read 200 bytes. This is where I want to read it into. So this is something on the stack. So we push EBP first, and then we adjust the what we just pushed on the stack with the displacement. And then we push the file handle or the file descriptor, which is just a number. When you're reading, 0 means standard in, which is the same thing as cin in C++. So this is how you specify, I want to read from the input, the default input file. Then you call read, you adjust the stack like that, and you're done. So when you look at this chunk of code, it is no different from any call to other subroutines that we have talked about. Now, you can do it this way, okay? But you can also do it in a way that is much more lower level. So, well, that's not right. It's much lower level than this, and it makes use of the concept of interrupts. So I will just kind of chew up a little bit more time to finish this part. It is the same thing as doing this. Okay? You might recognize this format, the format of this instruction. You move a 3 into EAX, and then you move EBP into EAX, and then we add V to EAX. So basically EAX becomes, that would not be right. Okay, move L $0 into EBX. This is going to be in ECX. And then we move L $200 into EDX. And this instruction, you might recognize it from some time ago. That would do the same thing. Okay, so let's go ahead and explain, okay, what is happening here? Why is this doing this? This 3 identifies file read request. So each request or each type of thing you can request from the operating system has a number to identify it. Okay, 3 is requesting a file read, 4 is requesting a file write, 1 is requesting a process to kill itself, to end, and a whole bunch of other numbers too. EBX is quote unquote the first parameter. This is basically the file descriptor. Which file to read from. ECX is the second parameter, which is where I'm reading it to. So this is the destination of where to store the bytes read. And EDX is the number of bytes to read, okay? How many bytes to read? Okay, so the magical part is the last one, okay? The first part is kind of easy because we are using one register, EAX, to identify the system service that we are requesting. It's just a number. The other 3 registers are just parameters. EBX, ECX, and EDX are basically the same parameters that we use in a regular function call. But this instruction is a little bit mysterious. What is int doing? It is called a software interrupt. Okay? A software interrupt is an instruction because we can write it in a particular program. But what this instruction is doing is triggering the same hardware mechanism as handling an interrupt. In other words, when this instruction executes, it will elevate the privilege level, and it will use 80 as a vector to go through a particular pointer stored in memory to go into a particular subroutine of the operating system. So the operating system at that point will get control. It will first examine what is in EAX. Oh, okay, EAX is 3, you want to read from a file. And then the operating system will then proceed to look at all the other registers. Well, let's look at EBX. Which file are you trying to read from? 0. Okay, you're trying to read from standard in. How many bytes do you want to read? EDX. And where do you want me to store those bytes? ECX. So when the operating system is all done, it will execute the RETI instruction, return from interrupt instruction, which means by the time I continue execution at this no-op instruction, the operating system is completely done with the entire operation. And on top of that, the privilege level, which was elevated when we execute the int instruction, is now getting back to where it should be. So as a result, now we can interface with the operating system using just one single address. This instruction here is the single point to contact and ask the operating system to do whatever. If you want to write to a file, you go through this. You want to read from a file, you go through this. If you want to start a new process, you go through this. If you want to kill a process, you go through this. Are we kind of doing okay so far with this topic here? Okay. So that's all I can go through today with interrupts and system services. So next time we'll go ahead and look at some sample programs and just okay, so how do we read from standard in, how do we write the standard out? Those are fairly easy once we understand the concept. All right, so I'm gonna stop the recorder, and if you want to go to the lab, so I can take a look at your program, that's what we'll do at the lab.